Continuing our discussion of water as it occurs in the ground, we need to go through quite a few more definitions. We need to slog through these because they're really important and they're commonly used, and you will need to know them throughout your career as a hydrologist. The first term that I'm going to define for you is porosity. It's commonly given the Greek letter phi or phi, or its lowercase letter n. And it is defined as the volume of voids over the total volume of a sample. This is equal to the sum of the volume of the air plus the volume of water in a sample over the total volume. So you can think of this as the ratio of the not solid parts of a sample to the total volume sample. Because remember, air plus water plus solid is equal to the total. There is a related term known as the effective porosity. And the key distinction here is that the effective porosity includes just interconnected pore spaces. So if you had a tiny pore that was inside of a grain, a solid grain, for example, that wouldn't count because it's not connected to the other pore space in the medium. And it's commonly denoted like this with a subscript effective or N effective. And so we're going to say that it's equal to the volume of interconnected pores. And by pore, I also mean void space. Over total volume. And what is the relationship between porosity and the effective porosity? Well, it is the case that the effective porosity must always be equal to or less than the total porosity in any particular sample. So this is sort of a description of the physical medium, and it doesn't really tell you where the water is or how much water is in a sample. For that, we rely on some terms known as the volumetric water content, given the Greek letter theta, most commonly. And it is equal to the volume of water over the total volume of a sample. And so obviously this term can change through time if the sample gets wetter or drier. And it will range from 0 at the driest state when there's no water up to phi, the porosity. Because recall that the amount of water that you can have in a sample is if it's entirely occupying all of the void spaces. You can't have theta be larger than the porosity itself. Another related term is the saturation state, usually denoted with the lower letter case, or the lowercase letter s. It is defined as the volume of water relative to the volume that the water could occupy, or the void space volume. And so S is going to range between 0 and 1, or you may see it expressed in terms of a percentage, so multiply it by 100, and you'll see it go from 0% to 100%. 100% implying that all of the pore spaces, all of the void spaces are filled with water. There's one more term to describe water that you'll commonly see in the literature, and that is the gravimetric water content. The gravimetric water content is commonly also theta, but sometimes it'll have this subscript lowercase letter g associated with it. And it is defined as the mass of water relative to the mass of solids in a sample. And so these are different terms. They are all interrelated with one another, but they're all different ways of describing the structure of the subsurface in terms of the amount of pore space that's in it and the ways in which water can occupy those pore spaces within the subsurface.